Okay, let's get started. So let's see. So we have today, then three classes next week, and then exactly one in-person class the last week. And what happened to the other two for the last week? I'm going to be gone, so what are you going to do instead? So we'll study, but what else is going to happen? Yeah, so I'm going to have video lectures, so watch the video lecture, okay? Any questions about anything? So only one more assignment, woohoo. Let's see, there are 3 labs left, so 11, 12, and 13, and final exam. That's all there is. So any questions about any of that? Yeah.
The 2-2 policy still stands for the final exam.
Yeah, it's exactly the same policy as the other 2 midterms. Exactly the same. Mm-hmm. Except now it's just all multiple choice. So, yeah, go ahead.
Practice final that's about to be out?
Yeah, I probably will. Yeah. But the thing is that, yeah, I could do that. It's just that it'll be multiple choice, obviously,
So
because
you're going to be down to
yeah. So I'm actually going to talk about that. So what you're going to get for the final exam, and I'm going to mention this at a later point again, just to reiterate it. You're going to get 2 things. So you're going to get an answer sheet and a packet which contains all of the multiple choice questions. So the answer sheet is the only thing with your name on it. The packet of questions does not have your name on it. So what you shouldn't do, and I've had this happen before, is students sometimes would circle the answers on the answer sheet, on the question sheet, not the answer sheet. And so it doesn't have their name on it, so there's nothing I can do. So when you circle an answer, what should you do in addition? Yeah, put it onto the answer sheet. So the answer sheet, actually I can show it to you. Let's see. Okay, we're back. So this is the answer sheet. Obviously I haven't fixed the date, so I'll fix that. But this is what you're going to get, and a packet full of questions. And that's it. So you put like A or whatever. That's probably not the answer for one, I don't know. So you put A, B, whatever, all the answers in here, and that's it. So effectively, for the final exam, you have to write at most 55 characters. So pretty simple. So it's not a lot of writing, obviously. But any questions about the final exam itself? Again, I'll talk about it more at some later point. Okay, so what have we been talking about so far? Pointers. And what did we most recently start talking about? Smart pointers. So obviously these pointers are smart. But why are they smart? So why are they called smart pointers?
Because they clean up the issues with delete and multiple references and a lot of things.
Right. So the issue that we had with pointers, with just a normal pointer, is that if we did dynamic allocation of that pointer, then at some other point we have to say delete that pointer or delete the array that we created dynamically. Whereas with smart pointers, you don't have to say delete at some later point, or even say new for that matter. So the good thing about that is that if you have multiple exit paths out to make the program stop or going outside the function, where we would normally have to put delete in all of those places, we don't have to with smart pointers. Because why? Because they're smart, but why? How? That's the important question. And a great final exam question, by the way. Why are smart pointers smart?
Because smart pointers hold their functions that declare the pointers, and they include protection against things.
They're not functions, but so they're objects. So they're actual objects. But when the let's just say the function exits, and you made a smart pointer on the inside. What happens? The destructor is called. So remember, whenever you have an object and it leaves the function, so like it's no longer in scope anymore, what is called? The destructor, not Ghostbusters. So the destructor is called, and what is on the inside of a smart pointer's destructor? The delete statement. So they're great in that no matter what happens, the program crashes, the function exits, whatever, whenever that object is not going to be used anymore, its destructor is called, no matter what. So smart pointers are great for that, yeah.
So instead of saying that like a smart pointer is a function, it's more of a template thing?
It technically is a template, but yeah, we haven't got to templates, but they are objects for sure. So it's an object wrapper around a pointer. So just like vector is a wrapper around an array, smart pointers are a wrapper around a pointer. They're exactly the same. Okay, so we talked about two types of pointers, unique and shared. I crossed this one out because this one is hardly in use anymore. So the two main ones are unique and shared. So what is a unique pointer at a high level?
A pointer that only has one thing associated with it.
Right, so there's this one resource and there's only one thing pointing to it. And nothing complicated there. If I want to change the ownership of this one resource to someone else, what do I have to do? Could I copy the ownership or do I have to move it over? I have to move it. Why? Because what kind of pointer is it? Well, in particular, what type of smart pointer? A unique pointer. Yeah, that's what I was going for. Good. So, but going back to your question, this technically is a template because of the angle brackets. So that indicates it's a template, but we'll get there eventually. So here we're saying we're going to create a unique pointer, and the thing that we're pointing to is an int. So, and then we call it uputter, and it's pointing to an integer that's created dynamically. And the great thing about C++ is that we can override operators to do different things. So we can say the star operator will behave the same way as it would for a normal pointer, even though this is just an object. So we can make it look like a normal pointer, and it behaves exactly the same. And so we get at least as everything that we could do with the pointer, but all of the advantages of not having to clean up after the memory mess that we make. But you see, okay, well here we say new in here, and I said that you don't have to say the word new. There's, in a recent version of C++, there's this function that basically does the work for you in calling new, so you don't have to do it yourself. You just call this function makeUnique with the thing you want to point to, and it'll do all the work for you. So it'll give you a unique pointer to something that was dynamically created. In this case, an int. So why is this better? Because you don't have to say the word new. That's the only reason. Yeah, so what about ownership of a unique pointer? So we saw that because it's a unique pointer, we can't just copy the ownership to someone else because we should only have exactly one thing pointing to this object. But we can move the ownership over. So there's this special function called move. We haven't talked about exactly what this does, but you can think of it as moving the ownership over. So it's taking the guts out of uputter and moving the guts over to uputter2. So uputter after this will be effectively useless. So it has nothing that it's pointing to anymore. Whereas uputter2 will get the contents of whatever uputter had before. So uputter2 before this statement will now point to the different object now. So if it was pointing to something else, now it's definitely pointing to this because a unique pointer can only point to one thing. Yeah, so uputter2 takes the ownership of the object previously owned and uputter becomes empty. So this isn't exactly what this function does, so I'm just letting you know right now. But in concept, that's what it does. But any questions about, yeah?
So would uputter be 0 or is it just empty?
It's empty in the sense that if you try to dereference it, it will be like trying to dereference nullputter, which means that your program will crash. Or the technical verbiage here is that it has undefined behavior if you try to work with uputter after this statement, because effectively it's an uninitialized pointer at this point.
So there'll be an address. It's just
Yeah, but it's just like there's no point in dealing with it anymore. Yeah.
Well, you would use the term null pointer to check for that, wouldn't you?
You could. So you could set uputter equal to null pointer after this. So I'm not exactly sure what'll happen here because you need to look up the move constructor, what it's called, of unique pointer. But just don't use uputter after the statement. It's undefined behavior of what exactly will happen. So only work with uputter 2. So in here, in fact, you won't ever really write a statement like this. You'll use a move like this in a different context. Namely, so if you are returning from a function a unique pointer, you call move on that. So it's moving it out of the function into someplace else. Well, since the function's about to return, you're not going to use the unique pointer that was declared inside of it anyway. So there's no real issue there, but it's just, yeah. So if you see something like this, don't use uputter, use uputter 2 instead. Okay, any other questions? Yeah.
for the make unique if you're not sure about what the variable type is.
Yeah. Oh, here? You have to know.
So you can't commit to it before we find out.
So I'm going to actually lie a little bit, and I'm going to say that you have to know the type in advance. In recent versions of C++, so this is the truth, you can get away with having uputter be a make unique of int in one place and a make unique of double in a different place, but it requires special things that are in very recent versions of C++. So for what you need to know, you need to put the type here. Yes. Other questions? Yeah.
So the data type goes into the little carrots.
Yeah.
So what exactly would go into the parentheses? Would it be the name or would it be the data type?
No, nothing for make unique.
Okay.
For make unique, yeah. So in fact, if you look at the function itself, so let's actually look up make unique. So let's look up make unique. Oh, it does take arguments. So let's see. So let's see. Oh, okay. So that's what it does. So what you would put in here is the arguments to create something of this type. So if I wanted to make an int with the value 42 initially, I would put 42 there. If I had like a student object which took a string name and a double ASU ID, you would put both of those arguments there. So it's the arguments that will create the variable here. Yeah, so there's this funky notation that we'll hopefully be able to see at some point in here. So we don't know exactly what this does yet, but basically what happens is if you actually look here, so it's returning a unique pointer of something, so some type. So in our case, it was int or student or whatever. And on the inside, it's saying new, then that type, so int or student or whatever. So ignore the standard forward thing. So what happens here is the arguments that are passed to make unique are passed to the constructor here. So notice, this is a constructor. So like if I was creating a student object, then this would be calling the constructor of student. So it's passing the arguments along. The reason why standard forward is here is technical reason, which we'll get to, but we're not there yet. But any questions otherwise? Okay, so what is this move function? So yeah, so it's required on the argument when you want to pass a unique pointer by value, because you can't copy the ownership for a unique pointer. Yeah, so if you're passing the unique pointer by reference, then you're still referencing the original one. So do you need a move then? Do you need to move the ownership in that case, if you're passing by reference? No, because it's still referencing the single unique pointer. You're not making a copy like with pass by value. So if you're passing by reference, there's no move needed. If it's passed by, if it's passed by reference, you do not need to call move. If it's passed by value, you do need to call it. In fact, it'll give you a compile error if you try to. Yeah, so a unique pointer can be returned from a function. The compiler automatically uses move. So you do not have to worry about the return, whether you call move on the unique pointer there. It's mainly when you're passing it in that it makes a difference. Okay, but this is not what the move function does, but it's conceptually what it does. So this was going back to our question earlier. So if we did this move somehow on this uputter object, so this uputter is effectively useless. If you want to actually manually deallocate it, you just set it equal to null pointer and everything is fine. Or .reset, so there's a function for it. You hardly ever do this, so you hardly ever use unique pointers anyway. But when you do, sometimes it's nice to say equals null pointer or whatever to fix the pointer to say, I'm not going to deal with this pointer anymore. Yeah.
The reason why I asked that question earlier was that when I was trying to use the find function.
Yeah.
One of the examples that I saw had checking to see if a pointer had the value of null pointer.
Oh, okay.
Essentially using a pointer as a flag of sorts.
Yeah, so it's just checking if it's equal to null pointer or not.
Yeah.
So that means that it's actually set to some address of some kind. So if it's set equal to null pointer, there's no point in dereferencing it because the program will crash.
That's what it was. So the find it was finding, and if it was set to null pointer, then the value was not found.
Yeah, so this is one idiom of programming, which is if you're looking over some structure, initially set it to some bad value, and then if you find the thing that you want in the structure, set it equal to the thing that you're searching for, and then return it at the end. Well, if it's equal to the bad value at the end, that means that it's not in the structure. So one technique of that for here is set it equal to null pointer first, and then if you find it, set the pointer to whatever you're searching for. And so therefore, if it's equal to null pointer, it's not there. So that's one way you can go. But any other questions? Okay, so you can use a unique pointer with anything. So you can have a pointer to an array, just like what have we done before. And then you don't have to use the delete square bracket thing that we talked about before. So it works exactly the same as the other unique pointer examples. So let's go on to shared pointers and hopefully get out of pointers soon. So what is the difference between unique and shared?
Shared and multiple references.
Right. So we have some resource, and any number of people can point to this object. Instead of just exactly one, we get a multiple. So can I copy ownership of a shared pointer to someone else? Yeah. So I can copy ownership of a shared pointer because any number of people can point to this, not just exactly one, which is nice. So how does the shared pointer manage everything? Well, it has this thing called a control block, which what it does is whenever you're trying to copy the ownership over, it increments some counter. So it maintains a counter for how many objects are pointing to the resource. So if we have 5 different objects pointing to the same resource, then the control block says there are 5 things. And then if one of the pointers goes away, there now are 4 things pointing to the resource, which is cool. So let's just say we had the situation of exactly one thing pointing to this resource, and it's a shared pointer. What happens when we deallocate that pointer? What happens to the control block? It goes to 0. So what can I do with the resource now? Is anything pointing to it?
No.
No. So what should I do with the resource? Call the destructor or delete the resource. Exactly. So that's how the shared pointer works. When the control block says there are 0 things pointing to this resource, we can free the object. We can call delete on it. So how do you create a shared pointer? Very easy. It's just like unique pointer. In fact, it's the same number of characters as a unique pointer. So shared pointer of int instead of unique pointer of int, and it works exactly the same way. We can create a different shared pointer from a different one. So I can copy the ownership over, so there's no issue there. And with make unique, where we could avoid the use of the word new, there's a make shared function. And good news there, you don't need C++ 14, you just need 11 here. So there's a make shared function and a make unique function. Make unique makes a unique pointer, make shared makes a shared pointer. Okay, let's see. So yeah, so be careful that all references to a dynamic object are tracked in the same control block. So be careful here. So this raw pointer is just a single pointer. It doesn't have a control block. It's just a normal pointer. Whereas here, these look at uputter 4 and 5. They're being constructed directly from the raw pointer, not from any other shared pointer. So these 2 objects are different control blocks. Whereas if I did this instead, so if I constructed uputter 5 from 4, the other shared pointer, then they're in the same control block, okay? Because it's being created from the from another shared pointer, so they maintain the same control block. So it's just I've never actually seen this in code, but it's just if you happen to encounter this, try to avoid having multiple control blocks, because if I free up uputter 4, then that'll delete the raw pointer because that's the only thing that's pointing to it according to that control block. But then that means that uputter 5 is still trying to point to this thing that was just deleted. So we get a dangling pointer as a result. So try to keep the number of control blocks to 1 if you can, if you're using shared pointer. Yeah, so try to use make shared if you can also, because it avoids the use of new and, of course, delete. Like with make unique, you can pass the parameters to construct the object if you need to. So if I wanted to set this integer to be 42, I would pass 42 into the constructor here. Okay. Whew, we're out of pointers, thank goodness. Any questions? And I hope there are none. Whew, thank goodness. My least favorite subject. So let's go on to actually doing something useful. So we're going to make classes useful again. Obviously a reference to nothing. All right, so what was the issue with classes? So with classes, so let's just say we forgot classes and we, not CSE100, but actual classes, objects. Could we do everything that an object could without objects? Yeah, so if we had some attributes of some object, like student has a name and ID or whatever, we can just maintain those in variables, right? Or if we had functions that are operating on those things, then we could just make them free functions. They're just normal functions now. So is there really anything that classes were useful for before? I would argue that they were useful in some ways. Oh, sorry? For encapsulation, yeah. So that is a good thing about them. What else? Yeah.
Decreases file size.
Yeah, I would say so, yeah. So if you, instead of writing out student 1, student 2, student 3, then I can just make, with all of their attributes in code, we can just put them into an object and just write one line for each of the students. So it decreases code size, yeah. But even more importantly, do you need to know how vector works on the internals? No. So what is the good thing about objects? Abstraction. So the classes hide all of the unnecessary details you don't need to know. It just hides everything for you, and then you just access all of the public either variables or functions. So, but that seems kind of annoying, right? In that, is that all classes are useful for? In fact, there are many other things that are useful for. So think of vector, for instance. So could we have a vector, let's just call it v, and I call v square bracket 0. Could I do that? Yeah. Could I do that with just like a student object? So if we just made a student class, could I call the student name square bracket 0? No. So what is special about vector? Vector is a class. So it really is a class. I assert to you it is. So why can I do square bracket 0 on vector? What's that? Well, I can put the student object in a library.
Because it's been chosen to allow it?
That's not true either. It's not been chosen to have it. It's because, go ahead.
I was just going to say, is it something that's defined in the class?
Very close. So in fact, we can override the square bracket operator to mean whatever we want to. So I could say square bracket 0 means access the name of the student. So I can define it to mean that. I can define the star operator to mean look at the GPA of the student. It probably wouldn't make much sense to do that, but I could do it. Which is why unique pointer and shared pointer, you can use the star on them to access the contents of the pointer, to make them look like an actual pointer. What about from, say, we're implementing a matrix. So we have a matrix class somewhere, and I want to define the operation this matrix plus this other matrix. Okay? So I want to define the operation this plus this. Well, could we do this? Define a method called plus plus and have the other matrix passed in as an argument and then do the computation there. Could we do that? Yeah, so it's just a normal function in that case. With C++, we can redefine the actual plus operator to say, do the operation this way. So in code, we can actually write the name of the matrix plus the name of the other matrix. I don't have to call some function. I can abstract away the details of that to say, I want to have this look like the operation I want it to do. I want it to look like matrix multiplication or addition, so I can redefine the operators to do exactly what I want. But I want to get to another thing. So I mentioned at one point that, actually several times, that if you look at this, so if I printed cout hello world, so maybe our first program, what is the type of this, the thing in the double quotes? Get to that. So we have assumed so far that it is what? String. But if we actually do look at the type of this, it's not a string at all. In fact, I'll invite you to figure out how to actually figure this out. It's a const char star. So it's a pointer to constant characters. So the thing that we have been working with all this time has been just a giant lie. But why can I do this? So why could we do this? So like I said, a string s equal to this, even though the thing on the right side is not a string at all. What, sorry?
You included the header?
It doesn't actually matter. Just because code is in a different header doesn't mean that the string class is just a class. So why could this work? It's been abstracted that way. In what way? Does anyone know? That is true in one sense. But what actually happens here is we can have a constructor that doesn't just take other arguments. We can just have a constructor which takes exactly one argument of, say, const char star, and it converts it into a string. So what it does here is we're abstracting the details away to say this equals sign, we can treat it as they really are the same, even though they're not. Which is why when we did the code before, when we had vector of int v equals some numbers like this, the thing on the right side is not a vector. But we can have a constructor which makes it look like one in this code right here. So the entire purpose of this is to make your coding easier and more intuitive. So you don't have to call this function, this explicit function. You can just write it naturally like this, or more naturally, I guess. So let's make classes useful. So one type of, so we've been talking about normal constructors. There are different types of constructors. So a copy constructor is a special type of constructor which takes exactly one argument of the same type. So if I want to create a string from another string, that is a copy constructor. Or if I want to create a vector from another vector, then that's a copy constructor. What if I wanted to create a, let's go back to the first example. What if I wanted to create a string from a const char star? Is that a copy constructor? No, because they're different types. So a copy constructor is when you're making an object from another one of the same type. So you're copying the contents from one into the other. So remember pass by value when I said that we're copying the value over? What do you think is actually called when that happens? The copy constructor. So when we make a copy, when we're passing by value, the copy constructor is called. So everything is starting to come full circle here. So in here, look at this right here. How many constructors at all are there in this CP class? There are two constructors. Yeah, so how many constructors are there? Just one, right here. Is it a copy constructor? Well, does it have one argument?
Well, yes.
Yes. Is it the same type as the class? Is the argument of type CP class? No, what type is it? Look at the type. What is it? Int. So is it a CP class? No, because they're not the same type. Okay? Int is not a CP class. If I instead, so ignore what's inside the constructor for now. So if I had a CP class v here, is that a copy constructor? Yeah, because it's the same type. Now, I'm leaving something out in that example, but it has to be the same type.
How do you compare a data type to like CP class in this case?
You would actually have to explicitly pass something in of the same type.
Oh, okay.
Now, that's a little bit of a lie too. So pretty much everything in C++ is a little lie. But there's something to do with like, well, what if I just had a single integer in here and I passed an integer in? Well, could it be implicitly converted to a CP class type? Then you would have to figure out, well, Do you want an implicit conversion like that, or do you want it explicit? So there's a difference there. But here, let's just say we're dealing with explicit. It has to be exactly the same type. So here it's not a copy constructor. So here, in this example right here, I'm creating a object C1 of just from an integer. So I'm normally creating it. So then here in this statement right here, I'm calling the copy constructor because I'm constructing C2 from another object of the same type, which is C1 in this case. So in this example, yeah, so here I'm doing a copy here. Oh, do I have, yeah. So, yeah, so I'm going to actually skip over these because they're not really that important here with regard to copy constructor. So what does a copy constructor look like? Well, here's the thing. Do I want to pass in, I'll actually just do an example and then we'll come to the conclusion we want here. So let's just say we have a CP class here and I want to make a copy constructor. So I make a public constructor and I'm going to pass something by, I'm going to pass a CP class here, C, and then I'm going to do stuff in here to do the copy. Well, what am I doing with the argument C here? Passing by value. Well, what happened with a pass by value? It calls the copy constructor to call the copy constructor. So it seems a little redundant here, right? So what should we do instead with this argument to avoid that copy? Pass by reference.
Would you want to make it constant as well?
I'm going to get to that.
Okay.
So you're ahead of me here.
Sorry.
You're not being paid to teach the class. So I am. So let's see. Well, do we want this? So I'm copying from this object to this object. Do I want to modify the original one? No, not necessarily. So the convention is to say const here because I don't want to modify the original here. So the const is here. But could I say it's not const? And I could modify the original. Yeah, so the convention is to put const here. You do not have to put const here. So if we look at this example right here, there are now two constructors, one of which is a copy constructor. Okay? Well, let's see, where are we in the slides here? It's so far away. So think about, so I'm going to reinitialize our nightmares and go back to the pointer slides for a second. So think about the move part right here. So I'm going to tell you right now, we'll get to it. This calls a move constructor. So we'll deal with like how it's being passed in a while. But when we do a move constructor, should the original be modified if we're moving from here to here? Yeah. So some constructors that take arguments of the same type, some of them should be const, like the copy constructor, because we're just copying from this. We want to maintain the original. Or we could move from the object, which means we should take the stuff out of it, which means that it shouldn't be const. Yeah?
So these constructors are included in like the pass by reference, pass by value, and the move functions, but why would we make them ourselves if they're already included in like other functions?
They're not actually, when you make your own custom type, you have to, well, not really true, but you have to write your own constructors here. So if you do anything particularly complex, you have to write the constructors yourself. So if you do anything that's not a default, you have to write the constructors yourself. And there's a certain rule of like which constructors you should do.
So for a class, so if we created a class, the ASU students class,
Mm-hmm.
And we wanted to pass by value that class, we couldn't do it unless we made a copy constructor?
Pass by value what thing?
The entire, the object. Like
So a copy constructor where we're not passing by reference. Is that what you're saying?
So I was saying, like, if we wanted to pass an ASU student
So,
object,
so what you're saying is doing this, effectively.
not exactly. I was saying if we're trying to use that in main, if we're trying to like use it in main, and we're trying to set equality, if we're trying to copy the values from one thing to another thing, would it not work unless we?
Oh, okay. So let's just say we had a CP class C1, and we initialize it whatever.
Yeah.
And then we wanted a CP class C2 equals C1 like this.
Yeah.
That calls the copy constructor automatically.
But if there's an automatic copy constructor like that, then why are we?
No. So if we do anything, so there's this rule where if you define any constructor at all, you have to define the other constructors. So there's a really fancy term for that. But so if I declare, like, say, the default constructor equal to do something special here, so I'm actually writing for it to do something, then I have to write the other constructors. If I leave all the constructors out, it does something that is what is called trivially copyable. So here, if I leave the constructor out entirely, then the copy constructor is implicitly generated. But even if that's not the case, so if we leave it like this, and so I do have to write a copy constructor, then what you can do here is, instead of defining it yourself and do all the work yourself, there's a nice feature where you can just say, I want to do the default thing. Whatever, so copy everything default. And how you say that is like this. So if you wanted to do everything without modifying, without doing anything different here, anything special, then you write default.
I'm curious why we didn't run into issues when we did our lab on the objects. Because we didn't write a copy constructor, but we did write default. Like we wrote two defaults.
I'd have to look at it, but it may be the case that the copy constructor was implicitly generated for you, so you don't have to worry about it. But you don't have to know anything about this. Just know that, get away from those slides. So copy constructor takes a const reference by convention of the same type. It's copying from another object of the same type. That's all it is. So when is the copy constructor called is pretty much all the examples we saw. So if we're passing by value to a function, or you're creating our C2 from the C1, that is doing a copy, or you're returning using a return statement. So that's another case. So those are primarily when the copy constructor is called. So the third one's not really true, but the first two are definitely true. Okay, so let's get to something fancy. Let's talk about operator overloading. So if we wanted to overload some operators to have them mean something else, then we can do something very nice here. So what you do is you create a function literally called operator plus, like this, or operator equals, or operator star, or whatever. So the name of the function literally is operator plus or whatever. Yeah, so what you do here is, there's a whole bunch of here. So let's talk about an actual example. So here's an example of an OP class. And then what you do is, I want to define an object of OP class plus another object of the same type. So what you do is you say, well, if I add an OP class object with another OP class, then the type that's returned is probably going to be, again, OP class. So you can think of this as like, if we have a matrix class, then we can define the operator plus between two matrices as one matrix plus another. What should be returned? What type? What type should be returned? A matrix. So that's why we say matrix here. So we can define it easily like this. And so inside operator plus, inside this function, we can do the actual arithmetic and then just return the integer. So in, let's see. So in main somewhere, instead of calling an obscure function like this, we can write really easy code and just say OP class or matrix or whatever, A plus B, and set it equal to S. So we can write it more cleanly this way. So even though it's doing other work under the hood, it looks a lot nicer here. Yeah.
So we could, like the example we talked about before, that's capable in Python, where you could swap two values by writing them like equivalent to one another. Could you actually overload it so that worked like it did in C++?
So you can only overload operators here.
Okay.
So there are gazillions of operators here, but I think you could. So you could overload, say, the caret operator, and then you would just write a statement like A caret B, and then what you do is you pass by reference the other object, and then do the swap on the inside. And so that could work too.
Okay.
Yeah, so you could do it, yes. Okay, so you can define operators this way. So the cool thing about operators is that when you're overloading them, the thing inside here, so I don't have to necessarily just add a matrix with a matrix. Well, what about, say, matrix multiplication? Could I have a matrix times a matrix?
Yeah.
Well, as long as the dimensions match. Yeah, we can do it that way. What about a matrix times a vector? Not our vector, but a single dimensional vector. Assume that the dimensions are okay. Yeah, so here, but those operations may or may not be different. What if we wanted a matrix times just a number, just a scalar? Could that work? Yeah, but those are fundamentally different operations. The cool thing here is that we can have an operator plus for an entire matrix, another operator times with a matrix, operator times with a vector, operator times with a double, for example. So you can have different operators depending on what you're trying to do. And no example of this is better than string. So if we wanted to say do this, so if we get rid of CP class here and just say, let's just have a string s equals hello, and then we couted s plus world, like this, and then maybe new line. So the type of s is what? It's not a hard question. What is the type of s? Yeah, s is a string. But look at this expression right here. What is the type of the thing in the double quotes? It's not a string, a const char star. So string overloads the plus operator to say, well, you can add two strings if you want, or you can take a string and add a const char star onto it. So you can have different operators work on different things to make the code much more readable. I didn't have to have some random function like append like this and then deal with it that way. So I didn't have to worry about that. I can just say plus and everything works as you might expect it to.
Wouldn't that be just the same as using the greater than sign again instead of the plus?
What do you mean greater than sign?
So like you do cout s.
Yeah. But the thing is, great question. So this is actually different. So what's returned, so cout actually overloads the double less than symbol to once it takes in one thing by parameter, which is s in this case, it returns another instance of the type of cout, which then deals with the next parameter, in this case the const char star. So these are different operations. So like it takes the string, then it takes this. Whereas before, if we did this, it does the expression first, then it passes it into cout. So it's a different expression there. Other questions?
But it looks the same, right?
But it effectively does the same thing, yes. Other questions?
So when you see out S again, it will give you hello world this time.
Yeah, so if we just print this, it'll print hello world. And
Like if the second line you just put S.
It'll just print hello and that's it.
No, I mean like.
Oh, like this?
No, like your original. You keep the original code. You add another line beneath it, and you just see out S. That would be hello world, right?
No.
Or
So
you put the plus.
oh yeah. So here the S plus world right here is not saved to a variable.
Oh.
So it's just an expression. Okay, I'll see you on Monday.